Hello dear students, my name is Vikas Agarwal and I am here to take your next session of the NSCP series. So guys, in today's session I am going to tell you about some astounding results of projectile motion, and you will be surprised and you will be awestruck to see the things that I am going to tell you and the manner in which we are going to derive them. Let's begin. So I would say the topic for today's session is some astounding results in projectile motion. Okay, so that would be your topic for today. Okay, right now guys, this session is relevant for a student who has studied projectile motion chapter. Whether you are a grade 10 student, a grade 11 student, or a grade 12 student, if you have already studied this chapter, which chapter? The chapter of projectile motion. It comes in grade 11. Okay, like officially as part of the CBSE curriculum, it is covered in grade 11. If you have studied this chapter, then this session is relevant for you. If you are yet to study this chapter, then you will not understand too much of what I am going to explain here. Alright, with that, let me begin. So first I will write down the things that you ought to know if you have covered the chapter. So what are those things? So okay, what you ought to know, like what are the things that you should know because you have studied projectile motion. So typically when we talk about projectile motion, we say that we have projected something with a speed u at an angle theta with the horizontal, and then this thing takes a certain trajectory and lands somewhere. Okay, and then we identify some parameters related to this motion. We call this as the range, the horizontal distance where the particle lands from the point of projection. We call it as the range. Okay, the maximum height attained during the flight, we denote it by h, and we denote tf is the time of flight. That means the time for which the particle was airborne. Okay, and the formula for this is something that everyone knows who have studied this chapter. So I believe you know that the formula for time of flight is 2u sine theta by g. Okay, the formula for maximum height is u square sine square theta by 2g. The formula for range is u square sine 2 theta by g. So these are the absolute basics of projectile motion, and I believe that anyone who has studied the chapter should be aware of this. There are other things that I am expecting you guys to know, but let's start from the most basic ones. Okay, so I will first list down the things that you ought to know. Then I will tell you the things that you may not be knowing, like there is a good probability that you would not be knowing those things. Okay, and then we'll see that the things that I'm telling you, how we can derive those results. Those are great results. Usually people do a lot of math, using the calculus to get to those results, but I will derive them completely devoid of mathematics, completely devoid of calculus, I would say. Okay, so this is one thing. Okay, now apart from this, what you ought to know, you should be knowing some results around R. Okay, so some results for R, like once you have obtained the formula of R, okay, then it can be proven that the range for angle theta and the range for angle 90 minus theta is same. You get the same value. So if this is horizontal ground, and let's say if a projection was made like this and another projection is made like this, okay, such that these two angles are complementary angles, that means adding them is going to give a 90 degrees. So let's say this is one angle theta 1 and this is another angle, this is theta 2. Okay, so if the sum of the two angles is 90 degree, then we get the same range. So that is one very important fact to know. Okay, the other thing that you should be knowing is that to get R maximum, okay, to get maximum value of R for a fixed speed of projection. That means you are allowed to change theta. You know, if I say that you will be projecting with the same speed u, but you are allowed to change theta, and you have to choose a theta that can give you a maximum range, then that theta should be equal to 45 degree, and the corresponding value of range is u square by g. Again, very standard results. It's not like that these are the fancy results that I was talking about. No, this is something that I expect all of you guys to know. Okay, what else you should know if you have studied the chapter? Next, you should be aware of the equation of trajectory. Okay, like the path followed by the particle, we call it as trajectory. And what is the mathematical equation of that? So if we consider the point of projection as the origin, so if we say that, okay, let's say this is x-axis, okay, and let's say this is y-axis, okay, so the point of projection is the origin. In that case, the equation of trajectory is written as y is equals to x tan theta minus gx square upon 2 u square cos square theta. Now this can also be written as x tan theta into 1 minus x by r, where r is the range. So these are the two versions of the equation of trajectory. Okay, so again, this is something that every student who has studied projectile motion from any decent place would be aware of this. And of course, the student should be sincere and hardworking. Okay, if you have studied from a decent place, but you were yourself not very committed, you were yourself not very sincere, then mostly you would not be doing these results. Okay, now what are the other results? Now I'm going to write some results, and these results, some of you would be knowing, some of you would not be knowing, and then I will write the results that most likely many of you would not be knowing. Okay, so what are the next results? So next I'm going to talk about projectile on an inclined plane. Okay, okay, so in case we have situation like this, let's say this is an inclined plane that makes an angle alpha with the horizontal, okay, and we are projecting, we are throwing something from the base of the incline at an angle theta, okay, like this, at an angle theta. Okay, then you know, the particle would follow a trajectory like this, like its parabolic trajectory would be cut short here, okay, and let's call it as L, okay, like the range along the inclined plane, let it be L. Now we can solve for the value of L, okay, but if I say that, okay, what is the value of theta that you will choose that can give you a maximum value of L, okay, then and what will that value be? So the value comes out to be u square by g 1 plus sine alpha, and the value of alpha, or the value of theta, the value of theta comes out to be 90 minus alpha by 2. Okay, so these are the results. You know, if you have to get maximum range along an inclined plane, then that range would be this much and theta would be this much. And in case if we are talking about down the incline projection, like if I say that you are projecting from the top of the incline and then you have to get a maximum range, then you simply change the value of alpha by minus alpha. You replace alpha by minus alpha in these results and you will get for the other case. So what I'm talking about is this. Suppose we have a situation in which an inclined plane is like this, okay, and we have to project a particle with a speed u at an angle theta like this, and we want to get maximum range out of this. We want to get maximum range. So this again we want to be maximum. So in this case, what you have to do, you have to just replace alpha by minus alpha here. So if I change this alpha to minus alpha, it will become 1 minus sine alpha, and here it will become 90 plus alpha by 2. So the corresponding results are that L max is equals to u square by g into 1 minus sine alpha, and theta will be equal to 90 plus alpha by 2. So these will be the results. So again, this is something that some of you would be aware. Now I was about to tell something. Yeah, you can check that if we say that alpha is 0, if we change alpha to 0, then we are again talking about the case of horizontal, like the projectile landing at the same horizontal level. That is the, we'll get this case, and you can see that our results match. If we put alpha is 0, we get u square by g, and this becomes 45 degrees. So this is a more general version of the previous result that we saw. Okay, now I expect you guys to know all this. Now let me talk about what are the results that you probably don't know. Okay, what are those results? Okay, so in this case, okay, I think you would not be knowing this. In this case, suppose the particle hits the inclined plane with a speed v, okay, and this is a speed u. Do you know that in this case, okay, in this case u vector becomes perpendicular to v vector? That means these two are perpendicular to each other. Okay, in this particular case, which particular case? When we get L as L max, and this is true here also. Here also the v vector, the final velocity, would be perpendicular to the initial velocity. Getting it? Okay, so here I will write what you probably don't know. Okay, let me write it. Okay, what you probably don't know. Okay, now you can write it in the comment whether I am right here or not. So you probably don't know that the two velocities are perpendicular to each other. Point number one. Okay, point number two, this is something that you would be knowing, but you may not have paid attention to it, that if the landing point is at a distance h vertically below the projection point, okay, then this is something that you would know, but I'm just putting it out. V will be equal to root of u square plus, this is simply the work energy theorem application. This is from work energy theorem, so this is something that you already know, okay, but I want to use it. Okay, this is work energy theorem. What else you probably don't know is this. The angle of projection, this angle, the angle of projection from the horizontal, okay, let's call it as phi. Okay, the angle of projection from the horizontal, okay, that angle, okay, that angle is like tan of that angle is v by u by v. Okay, so it is u divided by root of u square plus 2gh. Okay, this is again that you probably don't know. So now you know that where to project. Okay, I will derive all this. Okay, what else you probably don't know? You probably don't know that this L max will come out to be u square by g plus h. That's a very simple result. You know, the maximum range that you get on the same horizontal level plus the vertical distance h. Okay, so, and using this we will derive some fabulous results. So guys, these are the things that you probably don't know. Okay, now I'll try to derive all this. Okay, let's see. Okay, so now let's embark with the derivation. So I want your complete attention, everyone, and while deriving I'll show you that how you can use this knowledge to attack a lot of questions, especially the tough ones. You know, people who are trying Pathfinder, books like Pathfinder, and there are questions in that book which you find very difficult to solve. At least some of them, you will find that if you become good at this topic, you know, whatever I'm teaching you, then those very difficult questions actually turn into very easy questions. Okay, let's see. So as I promised, I will avoid calculus. So let's understand one thing, what is happening. Let's say you projected something with a velocity u. Okay, you projected something with a velocity u at an angle theta. Okay, at an angle theta. Now we can write velocity at any instant as initial velocity plus gt. Okay, because the projectile motion is an example of motion with constant acceleration, so we are free to use this equation. Okay, and this is the vector version of the equation. So what we understand is that u vector is a particular vector, it's a constant vector, but gt vector is increasing in magnitude with passage of time, and it is a vertical vector. Okay, so at t equal to 0, like right after projection, this value was 0, but then as time is passing by, okay, this vector is increasing in length. Do you understand this? Vertical vector which is increasing in length. And why am I drawing it from the head of u? because we want to add these two vector, and to add the two vector, what we have to do, we have to place one vector in such a manner such that the tail of one lies on the head of two, and therefore when I'm drawing GT, I'm drawing the tail at the head of U. Okay, so this is GT vector which is growing with time gradually, and at any general time, if I now join the tail of U with the head of GT, then that is my velocity vector. And if you think about it, that's what happens, right after projection, you see that the velocity vector starts turning like this. So that is what is happening. Do you see this? The velocity vector was like this, then this, then this, and then finally it becomes horizontal also. So this is a special moment, this is a special moment when the velocity vector becomes horizontal at this particular time, like when GT vector has become vertical, it is this much. At this particular time, the particle is at the highest location, and therefore the velocity vector has become horizontal. Okay, now by the time particle lands back on the ground, okay, this diagram changes to somewhat like this. Like, let me draw a bigger diagram. So if this is U vector, I'm drawing an exaggerated version, and if capital T is the time of flight, capital T, okay, then this becomes G capital T, okay, and then this becomes V vector, okay, and the angle of projection, we are denoting it as phi, the angle of projection from the ground, okay, let's denote it with symbol phi, okay. So this is the triangle that we get, the particle lands on the ground after time t, this is the triangle that we are getting, this is U, this is GT, this is V, okay. Now this is one key idea that we get this triangle. Next key idea is, if I want to write area of this triangle, okay, that would be half into base into height, okay, that would be half into base into height. So half into, here, see this length, can I write this length as U cos phi? This length is U, this angle is phi, so this is U cos phi, and this length is GT. So in this triangle, this length can become the base, and this can become the height. So half into base into height is U cos phi into GT. Okay, half into base into height is this. Okay, so this triangle was our first key idea. Okay, this is our second key idea. Our third key idea, like when you project a particle, okay, let's say you have projected it from a tower of height h, okay, and it lands on the ground, okay, it lands on the ground. So this horizontal distance, we write it as U cos phi into t, right? The horizontal component of velocity always remains the same, okay. So the range is U cos phi into t. So that's my third key idea. And now if you check the third idea and the second idea, okay, so we can write area as, okay, this U cos theta into, so U cos theta into t is R. So we can write it as GR by 2. We can write the area as GR by 2. That's my next key idea. Then my fifth key idea, the area of this triangle, it can also be written by using vectors. See, for any vector, like if this is a vector and this is a B vector, then the area of this triangle, the triangle formed by these vectors, it can be written as A cross B by 2 and magnitude of this. So likewise, if I look at this triangle, okay, then I should be able to write the area of the triangle as U into V into sine, okay, into sine of, let's say this angle is something, let's call it as beta for now. Okay, let's call this beta. So the angle between the two vectors is phi plus beta. Okay, so sine phi plus beta by 2. So that's our fifth key idea. Now A is this much and A is this. So from here we get that A is proportional to R. Okay, so using this 2 we can write GR by 2. GR by 2 is same as UV sine phi plus beta by 2. 2 gets cancelled. So range is UV by G into sine of phi plus beta. Now see this, guys. When the particle lands on the ground, the speed with which it hits the ground is independent of phi. Okay, we can confirm that from the work energy theorem. So when we change phi, V doesn't change. U is fixed, h is fixed. Okay, so if all these things are fixed, okay, so u is fixed, v is fixed, g is fixed. To get the value of r maximum, we need to make this as 1. We need to make this as 1, and because sine cannot become more than 1, and this will become equal to 1 when this angle becomes 90 degree. So we have now concluded, okay, we have now concluded that to get r maximum, phi plus beta should be equal to 90 degree, which means that v vector and u vector are perpendicular to each other. They should be perpendicular to each other. Okay, and not only that, we can now conclude that r max will be equal to u into root of u square plus 2gh, okay, divided by g. Got it? So we have just proved this. We have now proved that this distance is maximum, the maximum value of this is this much, and it happens when u vector becomes perpendicular to v vector. Like, we choose an angle of projection, okay, such that u and v become perpendicular. And if I go back here, see, if we have just concluded that this angle needs to be 90 degree, if this angle needs to be 90 degree and this is phi, okay, then this will become 90 minus phi, so this will again become phi. Okay, so from here we can get the value of tan phi also. From here you can see that tan phi, let me write it here, that means the angle that we should be choosing for projection, tan phi, from here perpendicular upon base, so it should be u by v, so this is the angle at which we should project the particle to get the maximum range. So okay, we have obtained is that, I'll summarize the results. Okay, I'll summarize the result, and then I will take you, like, I'll prove a lot of things. Okay, so if there is a tower of height h and we have been asked to throw a particle with a fixed speed from the top, but we have been given the liberty to choose phi such that the particle lands at a maximum distance from tower. Okay, such that the particle lands at a maximum distance from tower. It travels like this, and this distance should become the maximum. Okay, then tan phi has to be chosen like this. We have to choose a value of phi which matches with this number, with this equation, and when we do that, we will find r max as uv by g, that is u into root of u square plus 2gh by g. So this is what we are going to find. Okay, so that is one point. And also like, this is first result, this is second result, and the third result, that u vector becomes perpendicular to v vector in this case. Okay, now let's continue our discussion. So I'm going to give you a great argument now. Keep listening. So this is a tower of height h, okay, and you are projecting something from here with a speed u, okay, and you know that you can get a maximum range, okay, maximum horizontal range for a certain case. Okay, so this is r max. Okay, this is r max. This is the case we discussed. Now suppose I start drawing inclined planes passing through the point of projection. So this is one of the inclined, this is another incline that we can draw, this is another incline that we can draw, this is another incline we can draw. So we can draw infinite inclined planes. Here you are able to see that, I hope. Okay, we can draw many inclined planes through the point of projection. Okay, like we can draw 1, we can draw 2, we can draw 3, 4, and so on. So we can draw many inclined planes. Getting it? Okay. Okay, so we can draw many inclined planes. Now the one which is passing through this point, okay, suppose if the question would have been that, okay, I am giving you this inclined plane, let's say this angle is alpha. So the question says that, okay, let me give you an inclined plane of alpha. Okay, let me modify the question. So the question is now that I am giving you an inclined plane making an angle alpha, and I am giving you to throw a particle from this point and ensure that we get maximum range along here. Okay, let me go back. This is the inclined plane, this angle is alpha, we are throwing from here and we want to get maximum range along the inclined plane. I think this same trajectory will be answer to this question. The same trajectory will be answer to this question. Okay, like I have to ensure that I again throw the particle such that u vector and v vector become perpendicular to each other. So what I believe is that this trajectory and this trajectory, these two trajectory are identical. Okay, like in this case we will get maximum. Okay, so first understand the result. Okay, I am saying that if we had chosen an inclined plane like this, and if we try to get maximum range along the inclined plane, the same trajectory will solve our purpose. Why am I saying so? We can prove it by contradiction. We can say that, okay, let us assume that this trajectory is not the answer. There exists another trajectory that can give me a larger value of L. Okay, so what I'm saying that, okay, maybe there exists another trajectory that can probably give me a larger value. Well, if this is true, then here also the same trajectory should have given me a larger value of horizontal range. Then if there exists another trajectory that can give me a larger value of L, then my previous result is wrong, because then this trajectory, when chosen in this case, will give me a larger value of R max. But we proved that R max is maximum, like this is the maximum that we can get. If we prove this, so this has to hold good. If this has to hold good, then obviously this green trajectory does not exist, so it will not exist in this case also. So we have just proved that whether you make an inclined plane of inclination alpha and you try to get maximum range along the inclined plane, okay, or you choose a particular height and then you try to get maximum range along the ground, in both the cases you need the same trajectory. The same path will give you the answer. Okay, so now there is a lot of things that we have just proved. So this will be alpha, then if this angle is alpha, even this angle is alpha, this angle is phi. Okay, this angle is phi, this is v vector. So whatever results we wrote here, that results are now still valid. And if this is h, if this is h, okay, see, we prove this result that L max is u square by g into 1 minus sin alpha. This can be easily proved. We prove this using calculus. Now I am not doing that because most of the students are aware of this result. Let me but do some math here. So g times, I am taking this on the other side, so g times of L max minus g L max into sin alpha. Now from this triangle sin alpha, okay, how much is sin alpha? There is one correction here. This green trajectory is not useful for us, and this, just a moment guys, this L max needs to come, it needs to stop here. Now like the particle landed here, so okay, and yeah, okay, so sin alpha can be written as h by L max. See this, sin alpha perpendicular upon hypotenuse. Okay, so this, and this is equals to u square. So from here you get the value of L max. You get the value of L max as what? U square plus gh by g, or in other words u square by g plus h. This is something that I told you, a very simple result. Okay, that this maximum range is same as the maximum range on horizontal ground plus the vertical height h. Okay, got that? We were able to prove this. Alright, so I told you that what you probably don't know, okay, here what you probably don't know. So this we have proved that in this case, when we get maximum range along the inclined plane, the final velocity and initial velocity, they are perpendicular to each other. Okay, this is from work energy theorem, you should know that. This we have proved, this we have proved. So all the things we have proved. Alright, getting this everyone? And there's one more thing I would like to highlight. L max, we are currently writing it as u square by g plus h, and we also say that v square equal to u square plus 2gh. Okay, which means u square can be written as v square minus 2gh. Okay, and that would make this expression as v square by g minus h. So better remember this and this in a slightly different manner. Remember L max like this. It's u at the top. Okay, this is at the top of the projection, u top square by g plus h, or you can remember like v bottom. Okay, because when you come to bottom, this v would be higher. Okay, so minus h. So if you are using the speed at the top point, the two velocities are perpendicular to each other. If you are using the velocity at the top point, then use a plus sign. If you are using the velocity at the bottom point, then use a minus sign here. All right. Now next is this whatever we have derived here. Can we use that? Like, how is it useful in question? So you remember the result, guys. When you come across the question, you will be able to use it. I'll show you one usage. Okay, let me demonstrate, and that's a great usage actually. Okay, so let's talk about envelope of danger. Okay, now what are we talking about? Okay, suppose this is ground and there is a cannon mounted here. There is a cannon mounted here which can shoot in any direction. Okay, which can shoot in any direction, but the speed with which it will shoot, okay, that speed is u. It always shoots with a speed u, but it can shoot in any direction. Now we want to think about the region of space where this cannon can hit a target, like a flying aeroplane. Okay, so there would be a region of space outside which the plane would be safe, and there would be a region where it would not be safe. Okay, for example, what I suspect is there should be a curved region, there should be a dome shaped region. I don't know whether it is a circular, like a spherical, ellipsoid, a paraboloid, I don't know what it is, but I'm expecting that there should be a dome shaped region in within which it should be danger for the plane, and outside this the plane should be safe. An enemy plane flying, okay, is safe if it is outside this. So I want to figure out the trajectory of this. Okay, so this is, we are calling as the envelope of danger. Okay, so within this danger exists, outside this safety is there. Actually it depends on which side you are on. If you are sitting in the plane, then this is your safe zone and this is your danger zone. Okay, but if you are standing here and you are relying on this cannon to protect you from that plane, that's an enemy plane trying to kill you, then you will stand here and you will say that I am standing in my safe zone. This is my safe zone now. This cannon can protect me from this plane if I am within this zone. So whether it's safe or danger, that depends on which side you are on. Okay, now the question is, how can we derive the trajectory? So let's first anticipate that, what is this trajectory, like how is it coming? So like before we go into math, let's understand what is happening. So if I start thinking about the various cannons that we can shoot, the cannon, like various cannonballs. So if we shoot vertically upward, it goes like this and come back. Okay, if I tilt it a little bit, maybe it will follow a trajectory like this. Okay, then maybe a trajectory like this, then maybe a trajectory like this. Okay, then maybe a trajectory like this, it will go like this, maximum distance at 45-degree shot, then it will start reducing again. So there are infinite trajectories that we can draw. Okay, so I understand that the envelope would consist of, it would be the intersection, like it would be a curve. Here I think I lost the shape. Okay, but you got the principle, I guess. So it would consist of, these points. It would be, actually that looks bad. Okay, maybe I could have drawn a few more here. I've lost the dome shape here. So maybe, okay, so basically we can draw many trajectories. We can, okay, depending upon. So the envelope will encompass all this. Are you getting this? Okay, the envelope will be the one which, something like this. So think about one of the trajectory, any one trajectory. Let's pick any one. Okay, let's say this one. Okay, any one trajectory. So this trajectory, if it is touching the envelope, it will only be touching at a particular point. Like you can't expect, you're choosing one of the trajectory that can actually touch the envelope. It will touch at only one point, right? It cannot touch twice. Any one trajectory. This trajectory can touch the envelope only at one point. Okay. Now let this point be x comma y. Okay, this is x-axis This is y-axis. We want relation between x and y. If we get the relation between x and y, we are good. Okay, if I'm trying to look for the equation of this, that's a different story. We already know this. I'm trying to look for the equation of the green curve. Okay, now if this point lies on this green curve, okay, can I say that for this trajectory, if I consider an inclined plane like this, okay, for the pink trajectory, this distance has to be the maximum distance along the inclined plane. Like if I say that, okay, there was an inclined plane like this, and I was trying to get maximum range on the inclined plane, then this trajectory would be my answer, because no other trajectory can give me a higher range on this, which means, keep paying attention, I'll increase the thickness of the pen. Okay, this height is y coordinate. Okay, this distance should become L max, which is also the distance of this point from the origin. So it is also x square plus y square root of this, and from the formula we derived this formula. Okay, this formula I can write it as v bottom. Now this is the speed, the u speed is the speed at the bottom. So u square by g minus the height, that is y coordinate. Okay, so I obtained the relation between x and y. Let's do the math now. Let's square both the sides. So we'll get x square plus y square is equals to u square by g square of this plus y square minus 2y into u square by g. So this y square and y square gets cancelled, and the equation that we were looking for is x square, okay, plus actually minus x square, minus x, this minus will come this side, u square by g square divided by 2u square by g. So this becomes u square by g1, so it becomes u square by 2g. Okay, one of the u square by g gets cancelled, yeah, minus gx square by 2u square. This is your envelope of danger. This is the equation that we were looking for. Got it? So anything, and we now see that this is a parabolic equation. So we are now sure that this dome is parabolic. Okay, this is parabolic, and let's just check one thing. Okay, so I know from this point the maximum height that we can attain. Okay, that is u square by 2g. So if I put x equals to 0 in this equation, we are getting u square by 2g. And I also know that from this point, the farthest point that we can go is u square by g. So if I put y as 0, here, are we getting x as u square by g? I think we are getting x as u square by g. So this equation is perfect. So to derive the envelope of danger is a very lengthy process. Like any if you have seen any alternative derivation, you would realize that they are pretty long derivations. Okay, but this one seemed quite easy, right? Okay, so you can remember this. Okay, very easy derivation. You have to just give the proper arguments, and then you will find that it is quite easy. Okay, so I hope you enjoyed this, guys. And again, we can use this result. So let me give you a teaser. Okay, I'll give you a result and I will ask you guys to derive it. Okay, I'll give you a result, you try to derive it. Okay, so I'm talking about hitting two mangoes. Okay, hitting two mangoes in a single shot with minimum effort. Okay, hitting two mangoes in a single shot with minimum effort. So what is the situation? And minimum effort means least speed. Okay, what we mean least speed. Okay, so the situation is this, let's say there is one mango at a height h1, okay, and there is another mango at a height h2. Now they may be on the same tree, they may be on the different tree. I'm not drawing the tree, I'm only drawing the mango, and they are separated from each other by a distance L. Okay, now you are allowed to throw a stone from here, from here, from here, from this horizontal level, wherever you wish you can make the throw. Okay, so there are, boys, we have allowed them to throw a stone from any place they want, so they can choose their point of projection. Okay, now whoever can hit the two mangoes in a single shot, okay, and with least speed, there are multiple places from where the shot can be made. It's not that only a specific shot will do the thing. It's not like that. Okay, it's not like that. Like, it is quite possible that another person is also able to hit it from a different position with a different speed. It is quite possible. Okay, it is possible. But whoever hits the two mangoes with the least speed, okay, whoever manages to keep the speed of projection lowest, will be the winner. Okay, so what is this minimum speed that is required to hit two mangoes in the same shot? Okay, the answer to this is, the minimum speed that is required is root of g h1 plus h2 plus L. Okay, so h1 plus L plus h2. Okay, g. So this is the result. Now try proving this result yourself. Okay, hint, whatever we have done before this, that can be used to derive this result very, very easily. Okay, so try deriving this result. Alright guys, so I'll reiterate guys, whatever I've told you right now, you should practice it by your own hand, and once you practice it and you are able to derive it, then you will be able to use it in the questions also. And just in case, the best way to learn this would be that you try to explain this to someone. You see this session, you try to repeat it yourself in your rough copy, then you find someone to teach, then teach them all this. If you are able to successfully explain them the things, that person will learn from you, and more than that, you will learn from yourself. Like, you will become supremely confident, and during the process of explanation, you will find that a lot of your thoughts are now falling in place, like they are getting organized, and you'll be able to use these results for problem solving. All these results, when you use them in questions, there are multiple questions in Pathfinder book which can be solved using these concepts, and they can be solved very quickly. Otherwise, they take a lot of time. Okay, so I hope you like this session, guys. If you did, don't forget to like the session and share this video with your friends also. And also guys, we are operating NSEP batch, okay, Dhruv NSEP batch, in which I'm teaching topics like this every week, and we are conducting tests every Sunday, in which I give a paper on the NSEP pattern. That is 60 questions you get in the form of a test, and later you can use it as an assignment, and every week we are having discussion of those questions. Okay, so weekly 2 classes are happening, one for teaching things like this and the other for test discussion, and the test is scheduled on Sunday, and this will go on till the NSE exam in the last week of November. I think it is November 23rd when the exam is there, so it will go on till that. We'll also provide you some full syllabus NSE test. Okay, that batch is relevant for the students who aim to clear NSCP, who are targeting to clear NSCP this year. Okay, like if you have just moved into grade 10, then that batch will not be helpful for you. That batch is helpful for students who are already preparing for JEE either in grade 11th or in grade 10. Okay, grade 12. Particularly, it is useful for grade 12 students. Okay, because whatever I'm teaching there, that is the extrapolation of what you have already learned in your coaching or as part of your school study. So, with one class per week, I'll not be able to pick everything from the basic. I'll have to assume that you are aware of the things, and then I can give you great results in those topics, something that is not covered in the regular JEE classes. Okay, and you love them. I hope you love this too. Okay, see you every week. See you next week, guys. Take care. Bye-bye.